Okay, yeah, thank you. So my main topic for today will be 5D theories, but I was rushing so much at the end last time that I just wanted to give like a recap from 6D. So just to recap from the last few times, we can consider 2-0 theories, which are theories which have only tensor multiplets, and these have an ADE classification. So this is SUN, SO2, and E678, and they don't have those gauge fields, but they have some kind of tensor multiplet version of those gauge fields. In fact, if we reduce it down to 5 dimensions, we get these as gauge fields. But here we don't have gauge fields. It's like some tensor version of those. And these lead to interacting superconformal field theories in 6 dimensions. We could look at theories with 1-1 supersymmetry, and those lead to theories with only vectors, and those are all infrared-free. We can see that it's infrared-free because vectors are infrared-free, and also from the superconformal algebra, because there's no superconformal algebra with 1-1 supersymmetry. Another example class of examples that I looked at were M9 branes plus M5 branes, and that led to these theories that are associated with a small E8 instanton. They have an E8 global symmetry. I call them E8N. Some people call them E strings. They're superconformal field theories with 1-0 supersymmetry, and they have no vector multiplets, only tensor multiplets. And they have a direction like on their Coulomb branch where they go, for instance, to the A and 2-0 theories. And then the place where I was really rushing towards the end was about 1-0 theories that are made up from vectors and tensors. So we can have something which looks sort of like a Lagrangian. I should put this kind of in quotes, but where the scalar field of a tensor multiplet couples to the gauge fields. There's a coupling between the tensor multiplet and F wedge F, which participates in a Green-Schwarz, West-Sengadi type mechanism. And associated with that, the coefficient of this has to take some special value. There's no coupling constant here. That's part of why I wanted to put this in quotes, is there's no coupling constant here. There's something which has some quantized value. And this thing is related to anomalies. So for instance, for SU2, if we look at it with NF flavors, this coefficient C is 16 minus NF. And C has to be bigger than or equal to 0, because in order for this to make sense, in the end, we take some square root, and the square root only makes sense for a particular sign. So this only allows up to NF equals 16. Beyond that, it wouldn't make sense. And actually, there's some other anomaly considerations analogous to the Whitten anomaly that in this case tells you you can only have 4 or 10 flavors. Okay, so this is some class of theory. And if we had 16 flavors, that would be a case where this C is 0. And so there's no term like this. And so we don't actually need the tensor multiplet. And that theory is infrared-free. So if NF is 16, it doesn't give a superconformal field theory. It's just an infrared-free theory, whereas 4 and 10 would give us superconformal theories. And there's an analog of this SU2 thing for other SUNs. SU2 and SU3 are kind of special because they don't have a Cordic Casimir, and so there's kind of more freedom for them compared to the higher SUNs. For higher SUNs, starting at SU4, anomaly considerations only allow NF equals 2NC. So this is the only thing that's allowed by anomalies. And then there are various other possibilities that people have written down, like based on product groups, like quivers and things like that. Some of them were obtained from field theory considerations only. Some came from considering branes and singularities, also from F theory on Calabi-Yau threefolds. So there's a huge list now of 1-0 superconformal field theories. And in 6 dimensions, I mentioned also that we have these 't Hooft anomalies. And so these 't Hooft anomalies are useful because they can often be computed exactly for these theories. So they give us some exact information about the theories. Not only just about their 't Hooft anomalies, but there's this connection to the conformal anomaly A that also can be obtained. So that's where I wanted to leave off in 6 dimensions. Another thing about 6 dimensions was that this is, I mentioned in the first lecture from the classification of algebras, that's the highest dimension where we can have superconformal field theories. So this is like the highest dimension that we know where interacting conformal field theories exist. And so in the first lecture, I had some motivation for studying this, and someone in the question period also asked about the motivation. One motivation for this is just that it's tells us something new about quantum field theory, that these higher dimensional theories exist. But another motivation for studying them is that we could reduce down to lower dimensions and then get also new theories in 4 dimensions. And some of these new theories in 4 dimensions might be useful. So today I'll be discussing mostly 5 dimensions, but I just because of the thinking about the motivation, I wanted to mention a little bit about dimensional reduction. Also, just to remind myself to say some things about the connections to these theories. So we could look at what happens if we go, for instance, from the 6-dimensional theories down to 5 dimensions. We could put the theory on a circle and then ask what happens when we put the theory on a circle. And these are some general comments about what happens when you put different fields on a circle. Like if we have a scalar field in d dimensions, and then we put the theory on the circle to go to d-1 dimensions, we get a new scalar field, plus what I'll call Kaluza-Klein modes. I mean, they're not really like what Kaluza and Klein studied, but this is just like another name for these quantized momenta along the circle. So we have some quantized momenta along the circle which is like some integer over r, and those end up being some massive states from the point of view of the lower dimensional theory. If we have a fermion, when we reduce, we get fermions in general. We might get fermion or fermions depending on even versus odd. I mean, we have the same number of fermionic components, but it might not be it might not be irreducible. Plus also these Kaluza-Klein, analog of the Kaluza-Klein mode, so those would be some massive fermions. If we have a vector, when I say vector, I mean like a gauge field. So when we have a vector, we reduce down, we get a vector and a scalar. And in general, the scalar, if the circle has a non-zero size, in general, that scalar is periodic. Just because when we do gauge transformations to begin with, as long as the charges are quantized, the gauge transformations have a periodicity where if you go by a certain periodicity, that doesn't even change the phase of the wave function, because the phase of the wave function picks up some phase, e to the iq times the gauge transformation parameter. So if you switch the gauge transformation parameter by 2 pi, that's trivial. So you end up getting some periodic scalar, which you could think about as like the integral of the gauge field along the S1, which basically it's just the component of the gauge field along the circle, but the fact that you're integrating along the S1 is useful to think about in terms of the periodicity. And the periodicity here is like 1 over r. So as r goes to 0, you just get a non-compact scalar. And same way for a tensor. Like if we have a tensor, if we reduce it down in dimensions, we get a tensor in the lower dimension, plus we get a vector. So if we have this b mu nu, we can take b mu nu only in the lower dimensions, and so that's this tensor. Or we could take one of the components to be along the circle, and so that gives a vector. So this component where one of the directions along the circle is this a mu, which we could think about in terms of b mu nu as like the integral. Just like here, we integrate it along the circle. Here we integrate this along the circle. And that's useful to think about like how this depends on the radius when we write it that way. And yeah, so using this, we could look at, for instance, the reduction of some of these examples. Like for instance, we could look at our 2, 0 in 60. We could put the theory on a circle, and we get an n equals 2 gauge theory. In 5 dimensions. The tensor fields that we had in 6 dimensions are self-dual. So if we have a self-dual tensor, by self-dual, it's like h, which is dB, is star of h. And if it's self-dual, then we don't get both the tensor and the vector in the lower dimensions, because basically the tensor and the vector in the lower dimensions are the same. So this self-duality basically equates these two. So these end up being just like electric and magnetic duals of each other. Yeah, maybe just to say a little bit more about that. If we're in 5 dimensions, if we have f mu nu, so I could write this as like a 2 form. So this is some 2 form, and then if I take star of f, I get a 3 form. And the gauge field that we use to build this 2 form couples to particles. So this is like this thing couples to electrically, f couples to electrically charged particles, whereas when we take its star to look at its dual, we get H, and if we think of this H as like dB, this thing couples to strings. So strings, we can integrate the 2 form B along the string world sheet, whereas for particles, we can integrate the 1 form A along the world line. That says world line. So in 5 dimensions, electric strings are dual to magnetic, or electric particles are dual to magnetic strings. Anyway, so when we reduce the 2-0 theory down to 5D, we get an n equals 2 gauge theory in 5 dimensions. And the coupling constant G5 squared is proportional to the radius of the reduced direction. So maybe let's call the radius of the reduced direction, I'm always wanting to call it R6, but if we say like the coordinates go x0 up to x5, maybe I'll just call it R5. So this is the direction that we reduced. And we get this relation by thinking about here, how the gauge field is related to the 2 form with this factor of R. And this factor of R then leads to the fact that G5 squared is proportional to the radius. Okay, so that's one thing we can do. Another thing we can do is look at the 1-1 theory in 6D on an S1. And that also gives us to n equals 2 gauge theory. (5D). So the tensors, when we reduce from 6D to 5D, both the vectors and the tensors both give us vectors in the end, because the tensor in 5D is the same as a vector. So here we also get an n equals 2 gauge theory in 5D. And here what we have is, if we write down the action in 6 dimensions, we would have said there's a 1 over g squared f mu nu. And now when we go down to 5 dimensions, we integrate this over the direction that we've reduced. And so we get a factor of R5 over G6 squared. So if we just integrate this thing over the direction that we reduce, we get R5 over G6 squared, and that thing we identify as 1 over G5 squared. So here we see that G5 squared goes like, so here we see that G5 squared goes like 1 over R5, whereas here G5 squared goes like R5. And In fact, these theories have, I mentioned there's a little string version of this. And these theories in the little string version are related to each other by r goes to 1 over r, T-duality. And so that fits with the fact that one of them has a coupling constant that goes like the radius, one of them has a coupling constant that goes like 1 over the radius. And the other, and both of these cases are infrared-free. We know it has to be infrared-free because there's no superconformal algebra in 5 dimensions with n equals 2. There's only an n equals 1 superconformal algebra. So this is an infrared-free. So this illustrates that we could have a conformal field theory in higher dimensions, which when we reduce down to lower dimensions, it might just be some kind of trivial, boring theory. In this case, this is a very interesting theory in 6 dimensions, highly non-trivial, and then when we reduce it down to 5 dimensions, we get something that's a little boring. And here, this was kind of already boring, both in 6 dimensions and in 5 dimensions. Actually, if we reduce this case down to one more dimension, we get something that's back interesting again, because that's the n equals 4 theory. So if we look at the 2-0 theory on the torus, so if we say that we have some torus that we could picture as being like R5 and R4, then when we go down to lower dimensions, we get 4D n equals 4, where the tau, the gauge coupling, so this is theta over 2 pi plus 4 pi I over G4 squared, is the complex structure of the torus. And so this is a way to see that this tau has SL2Z symmetry. And we could see it also in connection with these formulas, because like here, G5 squared goes like R5, and so we would say that 1 over G5 squared is like 1 over R5. And then if we do the analog of this, going down to 4 dimensions, we get 1 over G4 squared is equal to R4 over G5 squared. So that's R4 over R5. And so we see that this has a symmetry where if we exchange R4 and R5, we take coupling into 1 over coupling. And that's strong weak coupling duality. That's S duality of the n equals 4 theory. So that's something that's interesting about one of the many things that's interesting about the 2-0 theory is that if you put the 2-0 theory on a torus, just the geometric symmetry of the torus becomes this highly non-trivial statement in about 4D n equals 4 that there's electric magnetic duality. So here changing the 2 cycles of the torus is like electric magnetic duality. So it's kind of just like thinking, it's the same torus, but we just turn our head to the side and it becomes electric magnetic duality. Okay. Yeah, let's see. I think that's all I wanted to say about some of these motivations. Yeah, so maybe... Okay, so now I'll mostly just focus on 5 dimensions. And actually, if you look at theories in even versus odd dimensions, it's like even dimensional theories are kind of reminiscent of other even dimensional theories. Like in even dimensions, we have anomalies and things like that. And odd dimensional theories are kind of similar to other odd dimensional theories. So some of the things that I'll be discussing today about 5D are similar to things that you heard about in Francesco's lectures on 3D. Like, for instance, in odd dimensions, we can have Chern-Simons terms. So in 3 dimensions, we write we start off with the thing that I was yesterday calling C2 of F, which is like trace of F wedge F over 2 pi squared, I guess with a factor of a half. And this is D of the Chern-Simons term. So trace and we can do a similar thing in for C3 of F. See, these C's of F's are just what you get by expanding e to the F over 2 pi. So that's where all of these factors come from. So here we'll have 1 over 3 factorial trace of F cubed. And this is D of some Chern-Simons, five-dimensional Chern-Simons term. So there's a term which is like A trace of A dA squared plus various other things like this term, like there's a term A to the 5th, stuff like that. So just like in 3 dimensions, we can add a Chern-Simons term to the theory as long as it has quantized coefficient, it's gauge invariant. Here in 5D, we can look at a 5D Lagrangian, which can have like this Chern-Simons 5 term with some coefficient k that has to be quantized. It has to be quantized for gauge invariance. Basically, the Chern-Simons form isn't gauge invariant, but its difference under a gauge transformation is something that has some integral condition. So if you look at e to the I action, that thing will be invariant as long as the phase changes by 2 pi times an integer. And so this 2 pi times an integer condition ends up telling us that this thing satisfies some quantization condition. So one thing that will come up in what I'll be discussing are some Chern-Simons terms. Unlike the 3-dimensional Chern-Simons terms are quadratic. Like this term here, this is cubic, but this term is quadratic. And the fact that it's quadratic tells you often that in 3 dimensions it leads to a mass term. There can be cases with Chern-Simons terms that don't have masses, but or where it leads to a conformal field theory, but in general you could think about, or roughly you could think about this as like giving some mass to the photon. And here, this is because this isn't quadratic, it's not like a mass term. So we still have like a massless photon if we have a theory with the Chern-Simons term. So there's some differences between 3 and 5 dimensions, but also similarities. Another similarity is that in 3 dimensions, you heard about in Francesco's lectures about how we can write down a global current associated with the UN gauge symmetry. So we have a UN gauge symmetry, and we can write down a global current where the global current is basically counting the magnetic charge. And here we can do something analogous to that. So in 5D, the analogous thing is we can write down a current J mu, which is epsilon mu nu rho sigma, let's call it kappa. Let's say it's proportional to this. Okay, so we could look at something like that to get a current. And this thing ends up being a conserved current. Basically, another way to write this is that we can write a one form and this one form using so we can write down star of J as a 4 form, and the 4 form is this same thing, C2 of F. And the condition that this thing is conserved, so d mu, j mu is 0, is the same as the condition that d of this 4 form, star j, is 0, that it's closed. And that's true about this f. Like this C2 of f, this thing is closed by using the Bianchi identity. Okay, so this is some conserved current. And the charge associated with this conserved current is instanton number. So this J mu couples to instanton. And the reason for that is that that's exactly what this C2 of f is. The integral of C2 of f in the directions transverse to the instanton are measuring instanton number. So instanton number, yeah, maybe I'll write here. This instanton number is the integral of C2 of f over the 4 transverse directions. So like in 4 dimensions, when we talk about instantons, these 4 directions are like the 4 Euclidean directions of space-time. But here in 5 dimensions, they could be the 4 transverse directions to the world line of a particle. So we can have some particle that's moving along in space-time. This is its world line. And so this is its time direction. And then if we integrate over space, we get the instanton number. And that's exactly what you do with the current. You integrate like the time component of the current over space. And so that's, if we integrate the time component of this thing over space, we just get the instanton number. And so this, in this current, by the way, because the instanton number, this thing here is an integer. So this thing is quantized. And because the charge is quantized, that tells us that the symmetry is a compact symmetry. If we do some analog of this thing that I was saying about gauge transformations being periodic, there's a periodicity in the gauge transformations. So this 5D, to summarize, in 5 dimensions, gauge theories. So I'm talking about gauge theories because I'm using like the field strength of that gauge field. So 5-dimensional gauge theories lead to a U1 global symmetry, and I'll write it as U1 with a subscript I, just to remind me to say that this is instanton number. So this is a U1 instanton number global symmetry. So this should be a symmetry of any 5-dimensional gauge theory. And so it'll actually it plays, the analog of this in 3 dimensions was the thing Francesco was talking about yesterday, about how you get this global U1 and you can relate it to like this periodic scalar and all of that. And so it plays some role in 3 dimensions, and this is an analogous thing in 5 dimensions. The analog in 3 dimensions, by the way, is instead of this being C2 of f, it's C1 of f. And you just go through the same thing with C1 of f, and then you get a global symmetry. In that case, C1 of f only makes sense if the group is abelian. Here, the C2 of f is there even for non-abelian theories. So we can have this C2 of f for, like, for instance, for SU2. Okay, so I think now I'm ready so far I haven't said anything too much using 5-dimensional supersymmetry. So now let's say some things about 5D supersymmetry. This stuff here would be true even if we had a non-supersymmetric theory. So 5D algebra. So we have the number of supercharges is I'll write it as 4 plus 4. The reason why I'm writing it as 4 plus 4 is that we have a supercharge with the spinor index, and the spinor index is like the 4 of SO5 or of SP4. So this is a pseudo-real supercharge, and we wanted to anti-commute to give p mu. And so p mu we get by anti-symmetrizing. This is similar to what I was saying also in 6 dimensions. And then because this thing is symmetric and this thing is anti-symmetric, we need to have more than one of them. And so the minimal supersymmetry would be to have 2 of them. So we have this like I and J, and here we can now make it have the right symmetry by putting an epsilon ij. So it's anti-symmetric in both of the indices, and so it fits with this thing being symmetric. And so that's the minimal supersymmetry, plus we can have central terms. And let's see. Do I want to write down the central? Yeah, so for instance, we can have Z, some central charge Z, epsilon, ij, we could have something like this as a central term, where basically this looks similar to the momentum term. And this is some central term that we could get if we just started in 6 dimensions and reduced down to 5 dimensions. Then one of those components of the momentum from 6 dimensions becomes like charge, which is like Kaluza-Klein charge, the Kaluza-Klein charge in 5 dimensions. So this would be like an example of a central term that we can have. We can have, actually we can have central terms for both particles and for strings. And again, particles and strings are interchanged with each other by electric and magnetic duality. Okay, so I mentioned also if we look at the conserved current, chalk. If we look at the conserved currents, at the top of the multiplet, so the conserved currents are 8 bosonic plus 8 fermionic, just like in 6 dimensions. And at the top, at the bottom of these 8 bosonic components are a SU2 R triplet at the bottom, plus at the top we have the current. So I mentioned in the first lecture how the conserved current has to be at the top of the multiplet to have the right algebra. There's a conserved current at the top, but a conserved current in 5 dimensions counts as 4 fields because it satisfies the conservation law. And so we have here 3 plus 4 is 7, and so we're missing 1. And what happens is that there's another scalar at the top plus scalar at the top. And this scalar we could think about if we came down from 6 dimensions as being like the component of the current in the extra dimension. When we reduce it down to 5 dimensions, we get an extra scalar. And these these scalars are interesting. So the fact that there's this scalar at the top is interesting because the dimension of a conserved current is always d minus 1, because if we integrate that over space, we should get a charge which is dimensionless. So it's d minus 1, so like in 5 dimensions, it's 4. And so delta of this scalar here, since it's in the same supermultiplet, has to also be 4. And that means that we can add a term in the Lagrangian, which is like mass times that scalar, that same scalar. And then it'll have the right scaling dimensions to be a Lagrangian. And so this is a relevant operator. And it preserves Lorentz symmetry because it's a scalar, and it preserves supersymmetry because it's at the top of the multiplet. So it's SUSY preserving. And actually it follows from the analysis of the algebra and the supermultiplets that this is the only relevant deformation. So this is the only operator for 5D superconformal field theories. So for instance, if we have a 5-dimensional superconformal field theory that has no global symmetries, then from this argument there can be no relevant operators. Or if we know that it has a global symmetry which is like E8, for instance, then we know that there will be these mass terms that are associated with E8. They actually would have to be, in that case, in the adjoint of E8. And so we would see that we could turn on these mass terms that correspond to like the Cartan of E8. And so if the global symmetry were E8, then there would be 8 mass terms that we can write down. So just to say as an example, E8 global symmetry. Eight masses in the Cartan. The reason why they're in the Cartan is because we can still use this global symmetry to kind of like rotate it to be diagonal. And so then, like if it were SUN, for instance, then these masses would be in the adjoint of SUN, and by a SUN global rotation, we can diagonalize it, and we would just get something that's in the Cartan. So if there's an E8 global symmetry, then there would be, for instance, 8 masses. Okay, so now I mentioned that if there's any time that there's a gauge theory, as I mentioned in the first lecture, I'm being pretty, I'm leaving off most of the references, but this thing about this U1I and this connection to the between the masses and the conserved currents was worked out in a paper by Nati Seiberg in 1996. So a lot of this is kind of based on this paper. Okay, so if we look at, for instance, this U1I global symmetry, if we make it supersymmetric by this argument, there's a mass term associated with that. So this U1I global symmetry will become a conserved current multiplet. At the top of the multiplet, there will be the U1 instanton number global symmetry, and then there will be a scalar operator. So we can ask, what's this scalar operator at the top of the U1I current multiplet? So this so at the top, there's this J mu, which is star of F wedge F. Let's just write it like that. So this is the instanton density. and its superpartner if we work out what it is, it's just the kinetic terms for the gauge fields, F mu nu, F mu nu. And that's not too surprising because like even in 4 dimensions, supersymmetry relates like the gauge kinetic terms to the thing that appears with a theta angle. That's why we get it in 4 dimensions, like a holomorphic gauge coupling. So here supersymmetry relates these. And this thing, so both of these things have dimension 4. So here I said the dimension of the scalar at the top is 4, and that's the right dimension for F mu nu because F in any dimension has dimension 2. And so F mu nu squared has dimension 4. So this says delta equals 4. And now if we wanted to add this kind of term in the Lagrangian, we say that the term in the Lagrangian where we turn on this thing is, we usually call it minus 1 over g squared. Let's put in the trace of F mu nu. And this is a relevant this is relevant. That's the same as what I was saying over there, and it's a relevant mass term. So usually we don't think about the gauge kinetic term as being a mass term, but that's the dimension that it has in 5 dimensions. So 1 over g squared in 5 dimensions has units of mass. And so let's just call this m0. So this is a mass. This is some kind of mass term. Okay, so yeah, maybe I should just draw here the picture that I'll try to discuss more like during the rest of the time. But just to have a picture in your mind, the idea is that we can have a 5-dimensional n equals 1 superconformal field theory. So imagine that we have some superconformal field theory like this. It'll have some global symmetry. And this global symmetry group might contain, for instance, this U1. So suppose this global symmetry contains as a subgroup this U1 instanton number as part of its global symmetry. Then it has various mass terms. All of the mass terms are associated with the global symmetry. One of the mass terms is this one that I'm calling M0. So if we wanted to, we could now deform this theory by turning on M0. So at this point up here, we have M0 is 0. M0 being 0 looks kind of scary from this point of view because it's like taking the gauge coupling to infinity. And so that tells us that, you know, if we wanted to think about it in terms of like a gauge theory, we're talking about a conformal field theory that's like an infinite coupling. And so that's what that tells us is that this might not be the right description of, at that point, of the conformal field theory. But there can be a conformal field theory for m equals 0. Conformal field theory should have all masses set to 0. And now we can turn on this m not equals to 0. This is a relevant operator. And when we turn on that relevant operator, we get at low energy something that's a gauge theory. With 1 over g squared is m0. And this, a gauge theory in 5 dimensions is infrared free. So as we float to the infrared, we just get free gauge fields if we just look at dimensional analysis. So we can have an interacting superconformal field theory that flows down to an infrared free theory when you turn on a relevant operator. So that's the picture that was argued for first in this paper that I mentioned from 1996 by Seiberg. Just right here. Seiberg, 96, considered the case of SU2. So the gauge group is SU2 with NF fundamentals. And argued that that for NF less than or equal to 7, so I want to explain where this 7 comes from. For NF less than or equal to 7, there's a superconformal field theory with an E NF plus 1 global symmetry. So like for instance, over there, I was abstractly talking about a theory with an E8 global symmetry as just kind of an example. But the idea here is that if we look at the theory with 7 flavors, according to Seiberg, that has an E8 global symmetry. So there are 8 mass parameters that we can turn on. One of those mass parameters, when we turn it on, it's this M0, and it takes us to the theory which in the infrared looks like SU2 with NF flavors. So there's this conformal field theory up here, which has an E8 symmetry. We could turn on one of the relevant operators, and then you get SU2 with, say, 7 flavors. So that's the punchline of what I wanted to argue for now. So now I'll give like some more of the details of where this comes from. But I'm tempted to ask if there are questions, but also just to keep plowing ahead because I keep looking at the clock and seeing my time is quickly going. Is there any question? Going? Okay. Okay, so these theories that I'm talking about have 8 supercharges. Maybe I'll just also say here that theories with 8 supercharges, they all have roughly similar moduli spaces. So yesterday I drew a picture of this moduli space where there was like a Higgs branch. The Higgs branch is where hypermultiplets get expectation value. So this is the moduli space. There's a Higgs branch, and then in 6 dimensions, I wrote it like this, where this was the tensor branch. So in 6 dimensions, this was the tensor branch. In 5 dimensions, the tensor multiplet just becomes a vector multiplet. And so if it's a vector multiplet, it's usually called the Coulomb branch. That's the usual name for it. And the reason why it's called the Coulomb branch is, so this is the Coulomb branch. The reason why it's called the Coulomb branch is because the vector multiplet has a scalar phi in the adjoint. A way to see that it has a scalar phi in the adjoint is exactly from this thing. The current has a scalar, and then if we couple the current to a gauge field, and so that gauge field, the scalar component of the gauge field couples to the scalar component of the current. So the gauge field has a field in the adjoint, and along this Coulomb branch, this field in the adjoint is not 0. So that's the Coulomb branch. And along this branch, some hypers are non-zero. The hypers are, for instance, like these flavors. So these flavors are hypermultiplets. hypermultiplets is just the name for the supermultiplet with this number of supersymmetries, for the basic supermultiplet with this number of supersymmetries. It's this thing that has 4 scalars. So, so we have the structure of a Higgs and a Coulomb branch, and the reason why this is called the Coulomb branch is because when you give an expectation value to the adjoint, you break the gauge group down to its Cartan subalgebra, U1 to the rank of the group. And the relation to what I was saying about here with the mass term is we can think about these masses as being like background fields for the global symmetries. So these masses are like the analog of these phi's for global symmetries. But here we're talking about something where there's a gauge symmetry. And so here this phi breaks down the gauge group to the Cartan subalgebra. And so it's called the Coulomb branch just because we have this U1 theory and there's like a Coulomb force between charged particles. So that's the Coulomb branch. Now, the analog in 4 dimensions is that there's, again, like a Higgs branch and a Coulomb branch. And in 4 dimensions, this Coulomb branch is something that's like a complex space. Like in the famous Seiberg-Witten paper where they studied 4D n equals 2, there was the U-plane, this complex plane. And you can write down an exact prepotential on the U-plane. So the analog here is that we can write down an exact prepotential on this Coulomb branch, but it's not a complex plane anymore because this thing in the adjoint is a real scalar. There's one real scalar. Like here, this is one real scalar. When we go down to 4 dimensions, what happens is that the other component of this gauge field gives the other real scalar that we know about in 4 dimensions. And that's how it ends up being complex. But in 5 dimensions, this is just one real scalar. So this thing is a space which doesn't have any kind of complex structure or anything like that. And so in fact, for the case of SU2, the Coulomb branch is just the positive real line. So for SU2, this is the picture of the Coulomb branch. So it's the positive real line. And the reason why it's the positive real line is because if we look at an adjoint of SU2, we can do like a Weyl reflection. So basically, like if we look at an adjoint of SU2, we could choose, like an adjoint of SU2 is like a vector in 3 dimensions. And so we can choose it to point along the z-axis. And if we choose it to point along the z-axis, we preserve rotations around the z-axis, so that's this U1. And choosing this thing to point along the z-axis means that it's proportional to the Pauli matrix, like sigma 3. And so we could take, for instance, like phi to be like phi times sigma 3. And then there's a symmetry, phi goes to minus phi is a gauge symmetry. That's part of just our rotation, if we can just do a rotation to take phi to minus phi. And so we should mod out by the gauge symmetries. And so, so we get like the real line modded out by the Z2, and so we can write this as like just the positive real line. So R plus the Coulomb branch. And at this point on the Coulomb branch, that's where phi is 0. So here we have an unbroken SU2. SU2, and here at other places, we get U1. So that's like when phi is non-zero. Yeah, so here I'm just writing down something in the adjoint of SU2. And so this is like, I can choose when I want to give it an expectation value, but there's a symmetry that tells us I can choose the expectation value along any direction. Yeah. So here, like the expectation value of this phi is the expectation value of that phi. Yeah, so for any non-zero phi here, we break to U1. And at this point, we have the full symmetry. Yeah, thanks. Okay, and so now we can write down a prepotential. And just like in 4D n equals 2, we can write down an exact prepotential on the Coulomb branch. And let's see. Yeah, the time, unfortunately, is basically up. Yeah, so we can write down an exact potential in the Coulomb branch. Maybe I should just write some final formula so I could point to it. So the prepotential is some function of, let's call it A, which is like the superfield that contains this phi. And it's at most cubic. So unlike in 4 dimensions, where it can have all of these higher powers from instantons, in 5 dimensions, it's at most cubic. And its derivatives give us the effective theory. So in general, what we can do is we can say that we have some scalars, some Cartan scalars, phi I, which are like this phi, for instance, is the one that we have for SU2. Then there's a gauge kinetic terms. So 1 over g squared is the second derivative of this prepotential. Maybe I'll just do it for SU2. I was going to write it for general gauge groups, but since I only have like 30 seconds, I'll just write it for SU2. So 1 over g squared is that. This this is also related metric for these scalar fields. So the kinetic terms for the scalar fields have this thing times d phi squared. So when I say metric, I mean the coefficient of d phi squared in the effective action. It's also this second derivative. And then there are Chern-Simons terms. The Chern-Simons coefficient, C, is the third derivative of this. And this thing has to be a constant. It has to satisfy some quantization conditions. And that's the reason why, that's one way to see why this thing can be at most cubic, is because the Chern-Simons terms have to be quantized. And yeah, maybe I'll just quickly write, just like in 4 dimensions, we can write some phi dual, which is the derivative of f with respect to phi. And this thing appears, maybe I'll just write here, like the central term for strings, magnetically charged strings, is like some magnetic charge times this phi dual, for instance. So this phi dual gives us the tension of strings, whereas the central term in the algebra for particles is n electric times phi. So at places where phi is 0, like for instance here, phi is 0, there's some massless electric field. In this case, the electrically charged fields are like the W bosons that become massless at this point. And then if there's some places where this phi dual is 0, then there's some strings that become tensionless. And if you compute what this C is for the case of SU2, so this thing could be computed exactly by a one-loop calculation. Like these Chern-Simons terms, when you integrate out some matter, you shift the Chern-Simons level in a way that's one-loop exact. And so this thing can be obtained using, this thing can be obtained exactly by a one-loop calculation. And so, for instance, for SU2 with NF flavors, you get, or Seiberg got that C was 8 minus NF. And so, for instance, if NF were 8, the C would be 0, as an example. And now, the condition to have this thing, so basically, maybe I'll write here, like the pre-potential maybe I'll just write this gauge coupling. So 1 over g squared is equal to the thing I was calling M0 plus 8 minus NF times phi. So what we see is that, and this thing has to be bigger than or equal to 0, because otherwise, this is like the coefficient of this metric. We don't want that to have the wrong sign, and we don't want the gauge kinetic terms to have the wrong sign. So in order for everything to have the right sign, this thing has to have a definite sign. And so what you see from this is that if NF is less than 8, you can take M to 0. So for NF less than 8, we can take M0 to 0. This thing will be positive because phi is positive. And so that's the superconformal field theory. And so this gives us back the SCFT. If NF is exactly 8, then when we take this thing to 0, this whole thing goes to 0. And actually, in that case, it's believed, like if we looked at SU2 with 8 flavors, it's actually believed to be, to complete itself to the theory of this 6-dimensional small Yade instanton. So the 8 flavors case is kind of a special case where it's actually not expected to be a 5D theory at all. Yeah, sorry, I think I already went 5 minutes over. But so maybe I'll just say in words very quickly that the fact that these things have this exceptional global symmetry follows from connections to string theory. So there are connections to string theory either by looking at M theory on Calabi-Yaos and looking at how the properties of the Calabi-Yaos, where you can have some del Pezzo shrinking, and the del Pezzo shrinking is related to this exceptional global symmetry, or it could be obtained from looking at the dimensional reduction of this M theory with the M9 brane, which ends up being what people sometimes call type 1 prime string theory. And there was a paper by Polchinski and Witten on this type 1 string theory, type 1 prime, and you can relate some parts of its moduli space to the heterotic theory, and then you can use results of Narayan and Witten, where you can see that you get this E and F plus 1 global symmetry. So the fact that there's this enhancement to E and F plus 1 global symmetry, this thing came from string theory. Like at this level, just in the field theory analysis, you wouldn't notice that. Sorry to go over.